Lastly, this number at the bottom of each element's entry on the table is the average weight of an atom of an element, also known as its atomic mass. Atomic mass is measured in atomic units, AMU. Each of these three particles that makes up an atom has a slightly different mass. Atomic mass units are incredibly small. Let's put it this way. A pineapple weighs 1 kilogram and a penny weighs 1,000 times less. Compared to the pineapple, atomic mass unit equals, that's a lot of zeros. Wow, this keeps going. Wow, atomic mass units are so small. That's why masses of elements are often weighed by the mole. By the mole? Ha ha ha. Not that type of mole. Hydrogen. A mole is a unit that equals measurement that equals 6 atoms. There is 1 mole of copper atoms and 22 pennies. Okay, I know how to understand each entry on the periodic table, and it says about the element. But where did the table come from? Let me tell you a tale. We'll turn back the pages of time. The tale of elements. That everything in the world is made of smaller building blocks. It's not a new one. The Greek philosopher Empedocles first introduced the idea and suggested everything we see, everything we are is made of 4 elements: earth, water, air, fire. Aristotle took the idea one step further and thought that the 4 elements were connected by 4 qualities. In 1808, the English chemist John Dalton designed a table of all the elements known at the time and ordered them by their atomic mass. Tables that organized the elements came and left through the 1800s. But the periodic table that has endured through the ages was created by the Russian chemist Dmitry Ivanovich Mendeleev. As the story goes, one night Mendeleev had a dream. In the dream, Mendeleev saw a huge table covered in cards, and each card has the name of an element on it. Before Mendeleev's eyes, the cards began to move, shifting and reorganizing themselves until at last they landed into place. Mendeleev awoke from the dream, as the story goes, and was inspired to try and recreate what he had seen in the dream. He got out small pieces of paper and, just like in the dream, wrote down the names of elements in them. Only 60 elements were known at the time when Mendeleev was trying to arrange his table, and he tried to get them all to fit into one complete pattern. Organizing and reorganizing these cards became a sort of a game to Mendeleev, and he desperately tried to arrange them in a way that made sense. As Mendeleev repeated this exercise over and over, he began to see traits like hardness and reactivity that repeated in set intervals as the elements increased in weight. If I line up the elements like this, all the elements in this column are dense, and all those in this column are brittle. Element traits were repeating like the notes of an octave. However, Mendeleev was trying to use all 60 of his cards with no gaps to make one complete table. Every time he did so, the patterns always fell apart until he realized, what if the more than 60 elements, by adding blank spaces that represent undiscovered elements into this pattern, it all snapped into place. This organization turned into Mendeleev's first periodic table of elements. It looks like a little different, but has a lot of the same information. Elements get heavier. It's flipped on its side but still has columns and periods, some of which are identical to the modern table. The word periodic means appearing or occurring in intervals. It is used to describe that repeating the nature of the elements that table highlights. Elements get heavier. Why is it called the periodic table? Mendeleev's table was also invaluable for its ability to predict the traits of undiscovered elements that he left blank spaces for. He used the traits of the surrounding periodic elements to make predictions about those missing elements. When he compared Mendeleev's predictions about a blank space he called ecosyllion to the actual trait that was eventually found and named germanium, his accuracy is staggering. Mendeleev was so confident that there were elements out there that matched predictions that he would tell scientists, dig deeper and you'll find them. And we have kept digging. Through research and experimentation, we've identified and isolated 118 different elements, almost twice the original 60 Mendeleev knew about. But as I said before, take one look around, wherever you are, and you'll find way more than 118 different substances. Elements react, mix, and join with each other to make all sorts of stuff that don't have their own entry on the periodic table, like marshmallows and fingernails, wood, sugar, plastic, slime, everything. All of the substances around us that aren't pure elements can be described as one of two things. A substance can be a compound. First, compounds are substances that are made up of two atoms from two or more elements that are joined together chemically. For example, two hydrogen atoms and one oxygen atom make one molecule, the smallest unit of a compound of water. Or a substance can be a mixture. When elements join together, they take on all new properties. One molecule of the sugar sucrose contains 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. On their own, none of these elements taste sweet, but together they're delicious. Compound. If you look at every single molecule of a compound, they'll all be identical with the same set of atoms all bonded together the same way. There are more than 10 million different types of compounds. What about mixtures? Mixtures are just substances that are just that, a mixture of different atoms and molecules that are not chemically bonded. Just like compounds, mixtures can take on new appearances and properties than what they're made of. Mixtures can seem compounds to the naked eye, but they're not. Mixture. When you look closely at the molecule that makes up the mixture, you will see that not every molecule is the same. Some mixtures are substances floating in liquids like water or oil, milk and salad dressing, peanut butter or oil paints. Other mixtures are tightly packed together and seem like they would be the same throughout, like paper, sand, or chocolate. But look closely and you'll still see the differences in molecules. While the recipe for a mixture like chocolate can vary, the recipe or formula for one molecule of water or any compound is always the same. There's a lot we can learn about the periodic table from understanding compounds and how they bond together. Chemical bonding in compounds happens between atoms that are trying to have a full outermost layer of electrons. This outermost layer is also called the valence layer of electrons. The electrons in this layer are the only ones that will react with the electrons in the outermost layers of other elements. Each layer of an atom can hold a certain number of electrons. The first layer can hold a maximum of 2. The second layer can hold a maximum of 8, and so on. So the number of electrons that a valence layer can hold will change based on how big an element's atom is. When an atom has a complete valence layer, that atom became chemically stable. This is a state that is highly desirable, and atoms may react with other atoms to give, take, or share electrons to achieve this stability. An atom that is only a couple electrons away from having a complete valence layer will try and gain those electrons to become stable. An atom that has slightly more electrons than a complete valence layer will be eager to get rid of its extra electrons to become stable. Come on, I just need one more electron. I'm desperate over here. I got 2 extra electrons here, and they gotta go. Any takers? Give. I could go either way. Take. When an atom is so close to having a complete valence layer of electrons, it will be more reactive than an element with a halfway filled valence layer that could just as easily gain or lose electrons. Through the taking, giving, and sharing electrons, multiple atoms are chemically bonded together, each one now having a complete valence layer of electrons. Oh, that's better. I had 1 extra electron, but now it's gone. I feel so mellow. Oh, that's better. I was going crazy almost having a complete valence layer. This extra electron really helped. There are 2 types of chemical bonds that form compounds. Ionic. Ionic bonds involve the giving or taking of electrons between one atom to another to complete their valence layers. Atoms that give electrons become positively charged. Atoms that take electrons become negatively charged. These now oppositely charged atoms are attracted to each other to form a compound, transfer the electron. Ionic compounds tend to have low melting points, are hard to brittle, and are good insulators. 2 examples of ionically bonded compounds are salt and baking soda. Covalent. The other type of bond that forms compounds is a covalent bond. These tend to happen between nonmetals and involves the sharing of electrons. This sharing sticks the atom together, forming the compound, shared electron pairs. Covalent electrons are typically soft and not good conductors of heat or electricity. 2 examples of covalently bonded compounds are water and sugar. The one thing that I don't know though is what starts a bond between the atoms. Does that happen when they get near each other? Sometimes all it takes is for 2 elements to be nearby. When iron is exposed to oxygen in the air, rust forms. Rust is actually a compound called iron oxide. Sometimes elements or compounds need to be added together in order for a reaction to occur. Baking soda and vinegar is both stable, but when added together, one of the byproducts is the compound carbon dioxide. Energy is in the form of heat and can also be used to kick off chemical bonds. Rubbing solid pieces of tin and copper together won't give you bronze, but heating them together will. Energy can also break down a chemical bond. In the experiment that we are trying to stop, the Pharaoh serpent, energy is added to mercury thiocyanate. which break down into carbon and various types of toxic fumes, which we don't want to happen. Is energy the only way to break a chemical bond? Yeah, once those elements are bonded and stable, it's going to take that energy to break that bond. If you put two electrodes into water, one negatively charged, one positively charged, the energy will break water and back down to hydrogen and oxygen. Light can also be used to break down bonds, like the silver nitrate we use for filming movies or taking photos. Okay, I'm convinced that you know what you're talking about when it comes to the basics of the table and atoms, but what do you know about the different sections of the periodic table? Let's start with what you know about my section of the periodic table. Hydrogen. I mean, you have always been one of my favorite elements. Sometimes you're grouped with other non-metals, but other times you're in a section all by yourself, like the other non-metal gases. Hydrogen is a colorless, odorless, and tasteless gas. With only one proton and one electron, hydrogen is the lightest element. Hydrogen is very reactive. When exposed to flames and oxygen, it explodes at room temperature. Haha, yeah. Watch out, will pop you off. Because hydrogen is lighter than oxygen and nitrogen, the main elements that makes up air, it was thought that it could be used in blimps. However, after the 1937 explosion of the Hindenburg airship in New Jersey, hydrogen seemed like a bad choice. A dark day in the history of hydrogen. Don't get glum. Without hydrogen, our lives will be totally different and not for the better. Hydrogen makes up 73% of all mass in the visible universe. It's the main element in the sun and gas giant planets like Jupiter. Since hydrogen is part of fat, sugar, water, and gluten, it's pretty much a part of every piece of food you eat. Yum and delicious. Hydrogen fuels us. Speaking of fuel, hydrogen is being explored as a new fuel source for the cosmic future. You know about my group of the periodic table, but it's not going to be so easy in the periodic fortress. Not all elements are friendly like me. Are you going to be able to keep it cool? I don't know. Well, you better keep it together because practice time is over. We're here, Mel. It's the periodic fortress. Whoa, this is spookier than I thought it would be. If there wasn't a maniac looking to give me a science test in here, this would be cool. Come on, looks like there's a weight on the left side. This element's character is not joking around, is he? No, not at all. We've got to be on our toes. He could pop out and quiz us at any time. A pop quiz? Okay, let's go. From here on out, I'll be counting on you. I need you to be my gun. We got it. We gotta be careful. This place is filled with monsters. Remember monsters? Yep, monsters that are made of the different elements you find in each section of the periodic table. Elemental said his lab was on his evil rooftop patio lab, so this fortress's layout is really an exact replica of the periodic table then. We'll need to go through the metals and non-metals and find a way to the roof to stop him. Whatever you say, Mel, lead the way. This seems easy enough. This place is so big, I'll bet we'll get through seeing a single monster. Look at them all, hydrogen. You and other elements I saw outside look so cute. I told you, Not all of us are friendly. Shh, get down. We're in the alkaline metals of the section of the periodic table. There's no use to trying to find a different path. We'll just run into more monsters. Or, what do you know about the alkaline metal elements as a group? Why, I thought you just needed me to leave through the fortress. There's something similar about the alkaline metals that we could use against them. Maybe you can make it through here. Okay, I'll try. The alkaline metals are in the first group, or column, in the periodic table, except you are hydrogen. As the name suggests, all of them are metals. There are 6 alkaline metals, and they are lithium, sodium, potassium, rubidium, cesium, francium. Wait, now, I should know this because I am an element. But why are some elements' chemical symbols so different from the name Mel? What does Na has to do with the word sodium? Some elements don't have chemicals in them that they're connected to their name, but they are. The chemical symbol from the sodium, Na, comes from the Egyptian natron, the natural salt mineral, because that's one of the first minerals that sodium was extracted from. The chemical potassium, K, comes from the Latin kalium, because potassium was first isolated from a mixture from plant ash and water. So you see, an element and its chemical symbol are always connected. So little of these elements have ever existed that we don't know really what it looks like. Right, this is the end. We continue part 3 later. Bye.